Recently, researcher Kang Sang from the Arizona-based LOL Observatory captured a brand new image. On the 2nd of November, he recorded the comet's presence using a 152 mm Ritchey-Chrysippus telescope. Notably, despite less than ideal observing conditions, Comet 3 I Atlas was already visible in the early morning sky. However, greater attention has been drawn to another image raising numerous questions. A fleeting glimpse of Comet 3 I Atlas captured by the Mars Reconnaissance Orbiter on the 3rd of October 2025. From approximately 27 million kilometers away from Mars, indicates data collection occurred between the 2nd of October and 3. Yet, subsequent portions of the data were locked or rendered inaccessible. This situation immediately sparked discussions about information transparency and scientific priorities. These images should represent the highest quality data humanity possesses of this comet. The delayed release or archiving of the data further intensifies concerns within the scientific community and legislative bodies. This data could have provided crucial guidance for continued observations of Comet 3 I Atlas before its eventual departure from the solar system. The public handling of this incident is troubling. NASA responded to Kim Kardashian's inquiry about Comet 3 I Atlas on the social media platform X, formerly Twitter, with only a brief reassuring statement: "No aliens, no threat." Despite formal requests from scientists and congressional offices for high-resolution imagery, these appear to have been either ignored or met with perfunctory responses. This stark contrast between rapid media communication and bottlenecks in scientific data flow creates an information vacuum. When scientific institutions promote their work through extensive channels, while simultaneously delaying critical data sharing with researchers, they cultivate fertile ground for rumors and public speculation. This disconnect in information delivery erodes public trust and delays the independent verification process that underpins scientific rigor. Unrestricted access to Mars orbiter high-resolution camera data is essential for rigorous analysis. Recently, public statements by Elon Musk reignited this debate. He suggested that certain natural celestial bodies might harbor abundant iron and nickel elements. While this observation holds some relevance, it overlooks a critical detail revealed by the 3 I Atlas comet data. Its nickel content far exceeds its iron content, a composition significantly different from known metallic asteroids. This leads us to two important inferences that must be clearly articulated. First, nickel of such high purity and with such a skewed iron to nickel ratio rarely exists naturally in isolation. It is typically accompanied by substantial amounts of iron. Mass separation of nickel and iron requires metallurgical processing and industrial technology. Producing low iron, high nickel alloys in practice involves complex processes like refining, electrolysis, chemical separation, and high-temperature metallurgy, procedures unlikely to occur spontaneously in the cosmic environment. Second, this exceptionally metal-rich composition casts doubt on the object's age and origin. Heavy elements like iron and nickel were scarce in the early universe. They formed within stars and were dispersed throughout space via supernova explosions. Thus, high metallicity typically indicates a later stellar generation, meaning this material is relatively young by cosmic standards. Thus, if the 3 I Atlas meteorite exhibits an unusually high concentration of industrial-grade metals, particularly nickel separated from iron-2 primary possibilities exist. Either it formed in a specific region of the cosmos or over an extended period where multiple stellar generations produced abundant metals, rendering it younger than many classical interstellar objects, or its metallic content was partially processed through some technological means. In short, its metallic composition and the purity of its refined metals suggest both a relatively recent formation time and possible signs of artificial processing, both aspects warranting deeper investigation. The non-gravitational acceleration exhibited by the observed 3I Atlas cluster demands rigorous physical explanation. If this acceleration stems from the recoil force generated by cometary gas outbursts, then according to the law of conservation of momentum, the object would need to lose approximately 1/16 of its mass, meaning hundreds of millions of tons of material would evaporate within mere weeks, forming a debris cloud detectable by multiple instruments. However, post-transit images have yet to reveal any massive cloud consistent with such a significant mass loss. This discrepancy between physics, space calculations, and observational results is precisely why scientists question whether we are witnessing an as yet unknown natural process or a potential indication of an active propulsion mechanism. The scientific community has organized an intensive observation campaign. Comet 3I Atlas will make its closest approach to Earth on the 19th of December 2025 and will undergo coordinated monitoring from late November through January. This period offers the optimal window to detect the hypothesized debris cloud, identify outflows, confirm their composition, and test competing hypotheses regarding their nature. Furthermore, the release and analysis of images captured by the Mars Reconnaissance Orbiter near Mars are crucial. These data will provide direct insights into its morphology, jets, and composition, offering a perspective distinct from that of Earth-based telescopes. The scientific community urgently requires this data, free from any political interference. Before drawing definitive conclusions, we must meticulously examine each anomaly that renders Comet 3I Atlas so unique. Each anomaly represents a fundamental deviation from established principles of cometary physics, and when combined, they form an unprecedented pattern that challenges our traditional understanding of natural celestial bodies. First, the precise alignment of its retrograde orbit with the ecliptic plane. Comet 3I Atlas travels along a retrograde orbit, moving in the opposite direction to the planet's revolution around the Sunday, yet it maintains precise alignment within 5 degrees of the ecliptic plane. In typical interstellar encounter events, celestial bodies typically approach from random directions in 3-dimensional space. The ecliptic plane covers less than 3% of possible approach angles, making such precise alignment statistically extremely rare. More critically, the combination of retrograde motion and precise ecliptic alignment suggests either an incredible coincidence or some force precisely targeting the orbital plane of our planetary system, retrograde solar jets. Between July and August 2025, Comet 3I Atlas formed prominent jets pointing directly toward the Sunday, creating what astronomers call a retrograde tail structure. This phenomenon contradicts fundamental principles of cometary physics. When a comet approaches a star, solar radiation pressure and stellar wind typically push vaporized material away from the star, forming the characteristic tail pointing away from the Sunday. The sunward jets from Comet 3I Atlas suggest 2 possible explanations. One is a physical mechanism we have yet to understand. The other is some form of active propulsion system overcoming natural radiation pressure, a phenomenon never observed in any known comet throughout centuries of observation. Third, extreme mass and velocity characteristics. Comet 3I Atlas possesses a nucleus mass approximately 1 million times that of Oumuamua and 1,000 times that of Borisov, yet it moves faster than both. In gravitational dynamics, larger celestial bodies typically move slower when launched from similar distances, dictated by the principle of energy conservation. This combination of immense mass and extreme velocity resembles observing a massive freight train overtaking a sports car, physically possible, yet requiring extraordinary initial conditions or an additional energy source. IV Precision Planetary Encounter Sequence. Comet 3I Atlas's orbit brought it into successive, meticulously timed approaches to Mars, Venus, and Jupiter. Crucially, its perihelion crossing was precisely scheduled during a solar conjunction, rendering it completely invisible from Earth during its closest approach to the Sunday. Such concealed approaches necessitate controlling arrival times within days of precision during interstellar journeys spanning millennia. This extraordinary accuracy suggests mission planning rather than random gravitational interactions. Industrial metallurgical characteristics. Spectral analysis reveals Comet 3I Atlas possesses a nickel to iron ratio vastly exceeding any known natural comet, with proportions closer to Earth's industrial alloys than primordial solar system material. Natural comets typically reflect the metallic abundance of their formation regions, where iron content far exceeds nickel. Furthermore, Comet 3I Atlas contains only 4% water by mass, an exceptionally low figure considering comets are essentially dirty snowballs composed of water ice and rocky debris. Unprecedented optical polarization phenomenon. Comet 3I Atlas exhibits extreme negative polarization of reflected light, a property describing the directional state of electromagnetic waves after reflection from an object's surface. Such intense negative polarization has never been observed in any other comet, including Comet Boreas, which displays typical cometary polarization characteristics. This intensity of negative polarization suggests its surface material or structure fundamentally differs from known natural celestial bodies, potentially indicating an artificial surface or unique material composition. Directional convergence with the WOW signal. The origin direction of Comet 3I Atlas lies within a 9 degrees celestial region of the famous 1977 WOW radio signal source detected by the SETI project. This 72-second signal remains the strongest candidate for extraterrestrial communication, though 9 degrees angular separation is relatively large. Its statistical significance is heightened by the signal's unique characteristics and Atlas's other anomalies. This directional correlation adds new complexity to an already improbable pattern. The eighth, anomalous spectral evolution. As it approached perihelion, Comet 3I Atlas exhibited a brightening behavior exceeding that of known comets, while simultaneously displaying a hue bluer than the Sunday itself. Typical comets brighten due to accelerated ice sublimation from proximity to the stellar heat source, yet their color remains largely constant or shifts toward the red wavelength band due to dust production. Comet 3I Atlas's blue shift suggests the presence of unusual surface materials or energy release mechanisms inconsistent with standard stellar heating patterns. The mass loss acceleration paradox. Observations by the ALMA radio telescope revealed non-gravitational acceleration phenomena, indicating that Comet 3I Atlas must have lost at least 15% of its total mass, approximately 5 billion tons of material, to sustain its observed trajectory. Such massive material ejection should have formed a detectable, extensive debris cloud, or coma extending millions of kilometers around the comet. Yet despite intensive monitoring, no such cloud has been observed. This presents a fundamental physics conundrum. Comet 3I Atlas exhibits acceleration typically associated with massive mass loss, yet shows no evidence of the requisite mass ejection. The foundation of scientific progress lies in data, and the vitality of data lies in sharing. Only through free circulation and complete transparency among researchers can science rigorously address the pressing core question: what we observe, is it an as yet ununderstood natural phenomenon, or something deeper and more unsettling? It all began with that set of images leaked from the Mars orbiter. And now we stand at a crossroads of science. The anomalous characteristics exhibited by Comet 3I Atlas are challenging our entire astrophysical interpretive framework. From its unconventional jet behavior to spectral lines rich in industrial-grade metals, these features render its natural origin explanation increasingly tenuous. Even its cosmic age is being re-evaluated. NASA's recent public response to prominent science media, coupled with comments from tech leaders like Elon Musk, underscores the urgency of accessing more raw observational data, particularly the unprocessed imagery and spectral records from the Mars Reconnaissance Orbiter. In the coming weeks, the scientific community faces a critical test. Can 3I Atlas's anomalous activity be explained by conventional debris cloud models? Or does it force us to re-examine the most fundamental assumptions of physics? The scientific community stands ready, awaiting the truth to emerge. Provided, data must flow freely. Share your questions and speculations in the comments section. Stay tuned for further developments, as the next discoveries may redefine humanity's boundaries around the concept of interstellar visitors.